look at some more details. First, the representation of the interference graph. We need to do both find all neighbors efficiently and check if a node is a neighbor to another node. So the latter we use a bit matrix, and to find all the neighbors we use adjacency lists. So both the representations are needed. The bit matrix is, of course, since it's an undirected graph, we only need to store it half of it, so to speak. Okay. Another detail which is very important is function call and return conventions. For each platform, a platform is a combination of machine architecture and operating system. For each platform, there is a set of rules which say in which registers the first parameters will be passed. Which register is used as the stack pointer? Where is the return value passed? And not only for integer registers, but the same parameters and return values for floating point variables, registers. Okay? So with coalescing, it's very nice to, what we want to do is to get the parameters, the variables which are parameters, we want them to be allocated a register in which they are passed. For instance, the first integer parameter is passed in R3 on a power machine, the second R4, etc. So it would be very nice if we can get the first parameter always in R3 without moving it to a separate register. And of course not starting with saving it to the stack and then loading it to some other register. Okay, this can be done very easily using so-called pre-colored live ranges. The pre-colored live ranges are the registers. And then what we want to do is to what we want to do is to coalesce a parameter with its corresponding pre-colored live range when possible. It's not always possible. And when we do that, we can avoid the copy statement. Okay? Another aspect to this algorithm is an improvement called optimistic coloring. And it's a simple modification to the shading algorithm. Instead of spilling a variable when we push it, when we do not push it to the stack, when we couldn't find, if we couldn't find a node with less than k neighbors, we normally spill it. But with optimistic coloring, we push it to the stack anyway and spill it only when we insert it back to the graph, if it couldn't find an unused color. Okay, another issue is something called caller versus callee save registers. When I said platform, that's the general term. For Unix, we talk about application binary interface. That's the contract between the programmer, if he uses assembler code, the compiler writer, the operating system, and the machine architecture. For instance, it says many things, but um, such as the layout of structs and bit fields, etc. But in particular, for this for register allocation, it specifies for what purpose each register is used. Okay, so for example, on power, we can start with the stack pointer. It's R1, thread pointer, R2, caller saved registers. A caller saved register is a register which the caller, I mean the function which makes the function call, must save before making the call. A callee saved register is the called function which must save and restore them if it intends to modify them. So what we can see here is that I mentioned that R3 is the register where the first integer parameter is passed. That's a caller saved value. That means if we have a parameter and call a function, then if we want to have that value of the parameter, I mean of this variable which is a parameter, then we need to save it ourselves, because the call function is allowed to modify the parameter. Okay, special for power is that register 3 is sometimes available as a normal register, and sometimes it's always has the value 3, the value not 3 but 0. Okay, so it depends on which instruction. Okay. So is it best to have caller save or callee save? Well, neither of them is optimal. If all registers would be caller save, then at each function call, there would be a huge number of save instructions, I mean store instructions, before the call, and the same number of load instructions after the call. And typically, most of these would be unnecessary, unless the call function modifies every register. Okay, so caller save it should not be used. I mean, the one who the committee which decides on the application binary interface should not only use caller save registers. Callee saves. If all would be callee save, then it's likely that the call function would save and restore a register which the caller does not care about. Okay, so therefore it's a mixture. Both caller save and callee saves registers are used for this interface. I mean application binary interface, this document. Okay, so more practical. When we decide on a color, when we come to that part of the shading algorithm, then it's a good idea to see if this variable is used across a function call. If it is used across a function call, it's better to use a callee save register and hope that the call function will not use that register. Instead of pessimistically using a caller save and therefore have to save and restore it before and after the call. Okay,